Summary. Let us summarize what we have learned in this chapter. Huygens' principle tells us that each point on a wavefront is a source of secondary waves which adds up to give the wavefront at a later time. Huygens' construction tells us that the new wavefront is the forward envelope of the secondary waves. When the speed of light is independent of direction, the secondary waves are spherical, and the rays are then perpendicular to both the wavefronts, and the time of travel is the same measured along any ray. This principle leads to the well-known laws of reflection and refraction. The principle of superposition of waves applies whenever two or more sources of light illuminate the same point. When we consider the intensity of light due to these sources at the given point, there is an interference term in addition to the sum of individual intensities. But this term is important only if it has a non-zero average, which occurs only if the sources have the same frequency and a stable phase difference. Young's double slit of separation d gives equally spaced fringes of angular separation lambda by d. The source, midpoint of the slits, and the central bright fringe lie in a straight line. An extended source will destroy the fringes if it subtends the angle more than lambda by d at the slits. A single slit of width A gives a diffraction pattern with a central maximum. The intensity falls to 0 at angles of plus minus lambda by A, plus minus 2 lambda by A, etc., with successively weaker secondary maxima in between. Diffraction limits the angular resolution of a telescope to lambda by d, where d is the diameter. Two stars closer than this give strongly overlapping images. Similarly, a microscope objective subtending angle 2 beta at the focus in a medium of refractive index n will just separate two objects spaced at a distance lambda by 2n sine beta, which is the resolution limit of the microscope. Diffraction determines the limitations of the concept of light rays. A beam of width A travels a distance a square by lambda, called the Fresnel distance, before it starts to spread out due to diffraction. Natural light, example from the sun, is unpolarized. This means that the electric vector takes all possible directions in the transverse plane rapidly and randomly during a measurement. A polaroid transmits only one component parallel to a special axis. The resulting light is called linearly polarized or plane polarized. When this kind of light is viewed through a second polarized whose axis turns through 2 pi, two maxima and minima of intensity are seen. Polarized light can also be produced by reflection at a special angle called the Brewster angle and by scattering through pi by 2 in the Earth's atmosphere. That's all in this chapter. Hope you have enjoyed it.